Hello and welcome to everyone. This shall be the final class during which we actually cover material. I have designated our class Monday, which is the last scheduled class of this class, to be a review session. So anybody who has any review questions that you would like covered from any point in the course, from any material that you may have encountered in the course, but I'm going to certainly give preference to topics that are exam related, shall we say, because it is intended as exam review, right? So, because the exam's on the 14th, so chop chop, right? But, so yeah, we're going to make that an exam review session, so if you have any questions, bring your questions, and we'll run it in that manner. Sound good? Good, 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 good. So, that's note number one. Note number two, I have absolutely no idea what the hell is going on with that Avenue quiz, so we're going to be marking it manually. There's an Avenue announcement about that, which you can read at your leisure if you wish. Yeah, I don't know. We'll see how it goes. Further to that, course evaluations. The course evaluations are a lot more important than people think they are. Things like hiring decisions get made on hiring decision and promotion decisions for people in teaching track anyway, are sometimes, like, certainly the course evaluations are taken into account for that kind of stuff. So if you hate me and you want to screw my career up, this is your perfect opportunity. Perfect opportunity to ratio the professor. Obviously, if you have some nice things to say, that would be nice as well, but the course evaluations are currently open. They'll be closing Tuesday. Honest feedback is always the best feedback because, you know, if you're not presenting the information, there's no way I can obtain it otherwise, right? So you should assume I know nothing, which is a pretty good assumption most of the time. And tell me what you think. Tell me what you think could be improved. Tell me what went well. Tell me what didn't go well. Even if you think I already know it, please just, spill the beans. I'm very interested to see what the course evaluations for this course look like. So, and I always read every comment. So, am I forgetting anything? I don't think so. Anyway. So, pursuant to that, we're going to launch directly into our discussion, our final discussion. We're going to be covering floating point and fixed point arithmetic in some depth. So, this will be following on from the discussion that we had of 2's complement that we had at the end of the lecture last time. So, I'm going to be mostly off slide for this one, so that'll be fun. So, how many of you have covered floating point representation in any degree of detail? Not one of you is confident enough to raise your hand, huh? Okay, so let's start with the basics, right? Binary numbers. This should be review. The way that binary numbers are represented is the same as the way that decimal numbers are represented. It's just, instead of the place values indicating powers of 10, they indicate powers of 2. That's the binary system. So, whereas a number like 2037 is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, times each of these guys, you take the sum of that, and bing, bang, boom, that's how you reconstruct the number, right? Same process for binary arithmetic, right? 101, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Multiply that out, right? Take the sum of all of that, and I know this isn't proper proper arithmetical notation, but that's okay, you're getting the idea, right? We have to cover this somewhat quickly. The reason it's called a base system is that it's talking about the base of the exponent that's used in either case, right? So, fine. So far, so good. So we are presented with the question, how does one represent real numbers inside of a binary arithmetical system? Well, the question we should be looking to is, how do we represent fractional numbers inside of a decimal system, right? So, and this gets confusing because probably all through grade school you were taught that a number with a decimal point is a decimal number, right? I'm here to tell you that's wrong. Any base 10 number is a decimal number, whether or not it contains a decimal point. It's the base that matters, right? So you'll hear me using some, some linguistic gymnastics in order to try to avoid calling numbers with decimal points decimal numbers. I will probably refer to them as numbers with fractional components. So, even if they're irrational, shut up. So in the decimal system, the decimal point indicates the point at which the powers of the base start going negative, right? So this is 10 to the 0, this is 10 to the 1. Past this point, we've got 10 to the negative 1, 10 to the negative 2, and on down the line. So far, so good. The same thing applies in the binary system. So, if we have 101.110, 2 to the 0, 2 to the 1, 2 to the 2, point, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. You multiply it out, you take the sum, bing, bang, boom. Does that make sense? So here's a question. How do you represent a number in the binary system like 0.1 base 10? Right? Well, essentially, you start off by seeing if you can do it with, 3 bits. That won't work. You'll get, something like 0.085, right? You'll try adding more bits. You'll get closer to 0.1. You'll add more bits still. You'll still get closer to 0.1 without actually hitting it. It takes an infinite series of binary digits to exactly represent the number 0.1 in the decimal system. This is the same effect as why you can't represent 1/3 in the decimal system. The essential problem here is that in order for a number to in order for a fractional number to have finite representation inside of a base system, that number must be expressible as a fraction with a power of the base as the denominator. Does that make sense? You guys need an example, don't you? Yeah, okay. So, yeah. Mind if I call up slides from a different course? I'm just going to do it quickly. And actually, I don't even care if you care. So, shut up. Because I've got this in another course. Because, like, we can't really talk about fixed point until we know what floating point actually is, right? And this is equally applicable to fixed point. Actually, we're teaching I am right now teaching you fixed point notation. So anyway, there we go. Good. So let's see here. We will go, right. So let's take, for example, this 0.1 and let's do it out the process that I described, right? So let's imagine, for the time being, that we are assigning 3 decimal digits to it, right? So the closest you can get to that is 0.001. Half, quarter, eighth, right? So 1/8. In decimal, 1/8 is equal to 0.125 base 10, right? So, not a very good approximation of 0.1. Let's add 2 more digits. This is more, right, than we need. So, it turns out, if you add 2 more digits, the closest you can get to 0.1 is 0.00011, right? That is 0.09375 base 10. Base 2, base 2. Right? So it's a closer approximation, but it's still not quite there, right? That's actually a fair ways from being there. So let's add more digits, right? Let's add an additional 4 digits. 0.000110011 base 2. Now, I'm not going to write the entire fraction here, but it approximately equals 0.0996. This is becoming a good enough approximation of this number for us to actually work with, if you're not concerned about holding too many decimal places. But this is not a reasonable amount of error for us to be able to perform computation in any real sense, right? So, the reason that this happens, right? Basically, how this is working, right? This guy is 1 out of 8, right? This guy is 3/32, right? This one, 51 out of 512. You can see the fractions become a closer and closer approximation as well, right? So the denominator here is constrained to always be some power of 2, right? It's whatever the most negative power of 2 that's used is. You with me so far? With me? Good. With me? Good. So, and obviously the reason is because you can't do like 0.2 here because you're working in whole integers, right? So that's not possible. So you're constrained to these types of approximations. So the more bits you add, the closer the approximation becomes, but you never actually quite get there. So, how many of you have a Python interpreter handy to you? 2 people. All right, I'll do it on the board then. Really? You guys just don't have a Python interpreter on your computers that you can just call up? What? And you did Python in first year. My God. Did they not even teach you how to use the bloody interpreter?
What is that?
Are you?
I'm genuinely.
We used to print a notebook
Are you pulling on my leg right now? You guys never learned what the Python bloody interpreter is? No. Okay. Well, all right.
Jupyter Notebook. It's not fast. It's kind of fast.
Okay. All right.
Hey, let's make it.
What the bloody hell are they teaching you? Okay. So I'll try to do it without expletives. All right. So, do y'all know the difference between a compiled language and an interpreted language? Yes. The Python interpreter is the program that interprets Python scripts, right? Python scripts aren't programs, they're scripts, right? So, the Python interpreter, if you download Anaconda, right, it is a command prompt interface wherein you can just enter Python code without actually having to put it in a file first. The way that Jupyter works is it takes your blocks of code and it feeds them into the Python interpreter when you hit execute. And it keeps one interpreter session running for the entirety of your notebook being open. That's why data transfers between different cells that you've run, because it's all being run in one interpreter session in the back end. Make sense? So when I say the Python interpreter, I'm talking about a command prompt which you can just enter Python code into, which, all right, I'll show you what it looks like. It looks pretty much the same thing in Windows or Linux. In Windows, it'll look more like a PowerShell session. Well, it'll be a PowerShell session, whereas in Linux, it'll be a Bash session. And if you're on a Mac, it'll also be a Bash session because Mac is a Unix-based operating system and supports Bash. So, good Lord. All right. There is a particular thing I wanted to demonstrate using the Python interpreter. Why would I assume that people just knew stuff? Why am I? All right. Okay, all right. Calm down. All right. Terminal. All right. In Linux, it's very easy. Python 3 brings up the Python interpreter, right? I know it's not, I'll get the links. So, interesting fun thing. Okay. What's 0.1 times 10? 1, yeah. What's 0.1 added to itself 10 times? I just said the same thing, right? I didn't in Python. So 3, 4, 5, 6, 7, 8, 9. Did I get the right one?
That's 11.
Is that too many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Da 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 da. Right? No, but it's not Python. It's actually this is a rare, very rare case where this isn't Python's fault. This is actually a problem with the construction of the floating point operations in the CPU itself. Every programming language has this: C, Python, C++, Java, whatever, right? The problem is that point 1 does not have finite representation under the binary system. It is a close approximation of 0.1, a very close approximation. It's a 16 decimal digit approximation of 0.1, which is small enough approximation that for most, in most cases, nobody would notice, right? But if you know a little bit about computers, you can tease it out by performing certain operations repeatedly. The error will accumulate through repeated operations, and you'll get interesting little cases like you add 0.1 together 10 times and it doesn't actually equal 1. Incidentally, this also throws off equality comparison. So, Rule number one that you should have learned in first year: never, ever, ever use equality comparisons on floating point numbers. For any reason. You always bracket, you always subtract them from the number that you're looking for, compare that to 0 using some kind of, like, use absolute value and look for it within a particular range. The range can be pretty tight, because again, you've got 16 digits to work with. But I'll show you what it looks like. I'll show you what actual proper floating point comparison looks like, right? So, yeah, so let's say that you have 1.0, right? X is equal to 1.0, y is equal to the result of that conflagration. All right, y is equal to that. All right, so x is that, y is that. X equals y is false, contrary to expectations. However, if you say the absolute value of x minus y is less than some epsilon, then that will become true, right? And you can make that pretty tight, and it'll still be true. But if you make it too tight, it will become false, because you'll hit the floating point error. This is what's meant by floating point error. Cool? Is this life-changing stuff? Are you ever going to use floating point equality comparisons again? Good. Then you will have learned at least one thing from my class that's useful. Because holy hell, if you're working on a project and you don't know this, and this is the problem you're having, you know, you would never know to look there, right? Nobody questions the structural integrity of the numbers, right? But in the case of floating point representations, that's something you need to be aware of if you're going to program for a bloody living. So, anyway, floating point. So if you, all right, I'm gonna get out. All right. So if you can do the same thing with 3, right? So, you know, if you have the number like 1/3, right, and you want to represent that inside of the decimal system, right, it's 0.333 if you're using 3 decimal digits to approximate it. That's equal to 330 out of 1,000, which is not quite 1/3, right? 0.33333 is equal to that fraction, which is again closer to 1/3 but not quite equal to 1/3, right? That's the effect. It works the same way going from a trinary number system into the decimal system as it does going from binary into decimal, right? You with me so far? Okay. So how the hell do computers even work then, right? If this is a little bugbear that's lurking at the bottom of every CPU that's ever been manufactured, at least one with floating point support, how the hell does anything even work, right? So let us talk about floating point notation. Floating point notation is an engineering compromise to try to square the need for range with the need for precision, right? So consider this, right? You're trying to decide a format for real numbers. Let's say you have 64 bits to work with, right? Obviously, the whole reason that we had that little Python gaffe is we can't possibly use an infinite number of bits to represent a number, right? We don't have an infinite number of bits. Computers are finite entities, right? And so are we. So 64 bits is like, it's the word size of modern operating systems. Even before modern operating systems, that was a useful size to have for operations like floating point. Like 64-bit floating point operations predated 64-bit operating systems, right? So basically, the thing that you have to decide, how many bits are you going to give to the fraction, and how many bits are you going to give to the number itself? Well, actually, I'm talking about fixed point. So let's talk about fixed point, then we'll talk about floating point, because fixed point is slightly easier conceptually. So so rather than 64-bit, let's say we had 8 bits, right? We have to decide where to put the decimal place, right? So if we put it in the middle, right, then we have 8 bits on this side and 8 bits on this side, right? So you can figure out what the smallest representable fractional number is by calculating 1 and then zeros all the way up to the decimal point, right? If you calculate the value of that in the decimal system, that gives you the precision of this numerical representation. And since we're talking about hardware suddenly, the number of bits that you're given in the register is a lot more loose than it is in a modern operating system environment where everything's pretty much the word size. So fixed point representations are pretty much exclusive to embedded systems design and like the hardware realm. That being said, if you can get away with 16 bits instead of 64 bits, then that's something you do because optimization, right? So the question is, what is the range of the number that you're trying to represent, and what precision do you need out of it, right? The range, obviously, is the size of this guy minus 1 bit for the sign, right? Now, using fixed point notation, y'all remember the discussion that we had of 2's complement versus the naive implementation? The naive implementation is sometimes called sign magnitude, because 1 bit is the sign and the rest is the magnitude, right? Believe it or not, that is still used in some places, despite the 2 zeros problem. It is also sometimes, basically you could expect to see either that or 2's complement, right? So, in either event, whatever the range of this is, you add like whatever the maximum value of that is, that's the maximum value / minimum value. You do some math, you figure out the range, right? It's based on the number of bits. You add more bits to this, you get more range. You add more bits to this, you get more precision. Make sense? Also a little bit more range, but fractional amounts of range. With me so far? Any questions? Questions? No? Okay. Good. So that brings us to floating point. So, in the scientific community, we have a representation for numbers which we call scientific notation, right? Under scientific notation, you have, some number times 10 to the power of some other number. Scientific notation. I'm sure all of you have seen it many times before. In binary arithmetic, we don't do it base 10, obviously. We do it base 2, right? So in binary, it's 2 to the power of some binary number, right? Make sense? We have a certain number of bits which are used to represent both the fraction and the exponent, right? we also need 1 bit for the sign. So, in 64-bit arithmetic, the number of bits that are assigned to both the fractional and the exponential components are fixed. This is actually an IEEE standard. It's standardized. There's a standards document. So in order for a hardware manufacturer to be IEEE compliant, they must follow the design of floating point numbers as laid out by the IEEE, right? This is very, very good because it means that 2 computers by very different manufacturers can communicate with each other without getting confused about what the actual values of their floating point numbers are, right? It's like standardization is very, very important. Everybody in this room should know that because we're all doing an engineering program, for Christ's sake. So, good. So, the actual breakdown, we used 11 bits for the exponent. We use 52 bits for the fractional component, which equates to about 16 decimal digits. And then we use 1 bit to indicate positive or negative. Right? Does that make sense? So, yeah, question?
Where did you get 16 decimal places from?
That's what it equates to if you were to represent it as a decimal number.
It's a based-time resolution of 16 decimal places.
Yeah, like the Python problem we had that we did that out to about 16 decimal places. That's what I'm talking about, yeah. Question?
For unsigned, where does that extra bit go?
For unsigned,
Yes.
there is no unsigned floating point representation. Not to my awareness, anyway. Yeah, there's no unsigned floats. There are unsigned fixed point, though. In fixed point notation, the signed bit is optional. All right? You can have unsigned fixed point. But because this has been declared by the IEEE, all floats have a signed bit. Make sense? So, good. Oh my gosh. So, I'll just tell you what the effective range of those mean. So, if you were to do out what the largest floating point number representable in 16-bit or 64-bit math, you would get 1.7976, etc., times 10 to the 308. So that's a very large number. It's like, just for scale, it's like if you had this universe contain another universe within every atom of this universe, and then that nesting went on about like 100 universes deep, that's the type of scale that we're talking about in terms of like how large that number is, right? The smallest representable number is 2.225 times 10 to the negative 308 in decimal arithmetic. So a very, very, very small number. So essentially, you're being hoodwinked, right? Computers cannot easily represent numbers beyond that range. You would have to write a custom library to do it. But the range is so incredibly large and the precision is so large that it doesn't normally come up. The only way that it comes up is if you have particular mathematical exceptions, like the one that I showed you with the repeating addition, right? There are other ways of doing it as well. If you try to add a number to a floating point number that is already very large and the thing you're adding is very small, that number can get gobbled up because it doesn't fit inside of the fractional component. and then it just disappears. So floating points can actually eat other numbers. But yeah. Any other any questions about any of that? Yes.
Is there a sign bit for the exponent?
Yes. Yeah. Yep. Double 100% for sure. Yep. Question?
What's the difference between a float and a fixed point? Like, is the one in binary a float, or is that a fixed point?
So this is float. This is fixed point. So the difference between a fixed point number and a floating point number is the number is directly interpretable without this times 2 to the operation. That's what makes it floating point. Like, the whole point of scientific notation is that you can basically move the decimal place around by specifying the power of 10, right? So in that sense, scientific notation is it's a notation which allows you to float the point. Make sense? Fixed point, on the other hand, is much more like what you might consider a traditional number. This point is stuck at the barrier between 2 to the 0 and 2 to the negative 1. It is just fixed there, fixed point. Make sense? Any other questions? Yes?
So what was the max number you said that could be represented?
Oh, it was 1.7 or 1.8 times 10 to the 308 power. Yes?
So for the fixed one, do we also have a bit in front to indicate positive or negative?
Optionally. It can be there. It doesn't have to be there. It could be just indicating the sign, and the rest of the number could be as normal, or the number could be in 2's complement. Incidentally, when this thing is in 2's complement, the whole number is in 2's complement, not just the part that's above the decimal point. Make sense? So, yeah, that's anyway. So that's what. Yes.
So floats can't be in 2's complement then, or can they be?
Oh, yeah. You know, it doesn't say here because they don't cover 2's complement in this class, but I think I could probably Google it quickly. Let's see here. Does float use 2's complement? Let's see here. So here's an article. Why floating point representation uses a sign bit instead of 2's complement to indicate negative numbers. So yeah, it uses a sign bit instead of 2's complement. Like, floating point operations are expensive, like in terms of hardware. Historically speaking, old computers had floating point coprocessors that were designed specifically to accelerate floating point operations. And one of the saleable metrics, I think I mentioned this before, one of the saleable metrics of a computer in the 90s was how many flops it was capable of, which is floating point operations per second. So you had computers with like 100 kiloflops and 20 megaflops and all kinds of stuff like that. So the floating point, like it was like in the manner of this class, it was like a separate IC component that they would that was at one point adjacent to the CPU. They over time saw a greater and greater degree of integration into the CPU, which culminated with the adoption of 64-bit operating system word sizes, which allowed the full integration of floating point into the operating system, because you no longer had to, double registers up in order to provide enough information into it. Like back in the day, under 32-bit math, or let's go back, because they also had 32-bit floats back in the day. under 32-bit floating point arithmetic, it took 2 cycles to load one of those numbers because everything was the word size of the operating system was 16 bits, right? So floating point operations were very expensive, which is one of the reasons that the Nintendo Entertainment System basically has very minimal float support. Basically everything going on in the NES is like pure integer arithmetic, which is kind of cool. Any question?
Yeah, so for like the, I don't know what to call it, like the point, or like,
Yeah.
I don't want to call it the decimal point because that's
Yeah, just call it the point.
Yeah, the point, right?
Yeah.
So can it be moved like inside the fractional component of it, or is
Not
it?
in float.
Okay.
Yeah. You move it by modifying the power.
So then how do you get like the max number that was like 1.8 times 10 to the 308?
This is all ones. This is all ones,
Okay.
except for the sign bit.
Okay.
Yeah.
So for the binary one, would it be 1 point and then like just all ones after that?
Yeah.
Or- okay, so you can only have one number before the point.
Yes.
Okay.
Just like in scientific notation.
Right.
Make sense? Good. Any other questions? Yes.
Just about the, how does that actually represent 1/8
Sure. So 2 to the negative 1, right? 2 to the negative 2, 2 to the negative 3. Multiply them out. So we've got 0 times 2 to the negative 1, which of course cancels, plus 0 times 2 to the negative 2, which of course cancels, plus 1 times 2 to the negative 3. 2 to the negative 3 is of course 1 over 2 to the power of 3, which is 1/8. Awesome. Quick maths. Any other questions? Yeah, I don't know if I have anything else that's useful to say about. I could demonstrate that thing where a floating point number can eat another number. Do you want to see that? It's just kind of cool. All right. Yeah. There we go. So, right? Yeah. Oh, it's wrong block. There we go. Right? So what's going on with this example? As an integer, this is an acceptable integer. And one of the things that Python does in the background, actually, is it will extend the length of integers that you use that overflow, and it'll just assign more memory to it and do more work for you in the background so that you don't even have to understand that bits even exist. But it can't do that with float. So under integer arithmetic, you get what you expect. Under floating point arithmetic, this guy, which is 1 times 10 to the 19th power, if you add 1 to that, that 1 drops off the end of the fractional component without being registered. So, if you back convert that into an integer again, you don't actually get the 1. The 1 disappears. Boom. Right? Yeah. So So there's one thing that you have to be careful of with this type of representation. You might be saying to yourself, well, when does stuff like this actually happen? And it's like, yeah, I can see that, but you only need to hit 10 to the power of 16, first of all. And second of all, think about multiplication. There are some formulas, such as the quadratic formula, that'll square a number and then divide it by something else of similar size, right? Or you can have lots of algorithms like we'll square a number and then take the square root of it, right? Think Pythagoras. If the square here hits this kind of size and the other thing doesn't, right? Like if in Pythagoras, if like a squared ends up being 1 to the, the guy, and then the other one is, just 2, 2 gets eaten. And you might be saying to yourself, well, it wouldn't have mattered much anyway, because if you think about that triangle, that is not a triangle that exists in physical reality. But it's the principle of the thing, Why should we subject ourselves and suffer the effects of inaccurate mathematics when we can have more exact mathematics? But perfection is also not for this life. So yeah, I guess this is it. Thank you very much for attending class this semester. Yeah, you can hit that. Are we off the record?
No.
No? Okay, hit it. All right.